when a number of small identical drops of known radius, obviously, combine to form a big drop of unknown radius, how much work has to be done or how much energy has to be supplied for this is the kind of a question that we would like to look into, right? So when there is energy or work involved, we shall define surface tension basing on that in terms of that work and energy. How can we define that? If you remember back our definition, surface tension can be defined as work done in producing a unit change in the surface area of the liquid, delta A. That implies work done or energy supplied is surface tension into delta A. Here, surface tension is shown the letter T for the convenience. Delta A means area final minus area initial, or area big minus area small. So, what is given in the problem? Number of the small identical drops. Let me illustrate what does it mean by there are so many drops. So many drops. Each of known radius r. Let the number of drops is n given for you. They're all coalesced, combined to form a big drop. But the radius of that big drop is not known for us, is not given for us in the problem, unknown. In that case, I want to calculate work done. But one thing I would say, let's imagine, let's assume that the radius of the big drop is r. Of course, it's not known for us. So finally, I shall eliminate the term because it's not known for us. Now, but we need to know one point clearly, right? This is, I can apply conservation of mass. The definition of a density, if you remember back, density equal to mass by volume. For a given liquid at a given temperature, density is constant. Mass is also constant or conserved. So as density and mass are conserved, it implies it's obvious that volume is also conserved. What do you mean by volume is conserved? When n drops of identical radius are combined, they together will have a certain volume. They converge into a big drop that also will have a bigger volume. As volume is conserved, what we can say is volume of all small drops together shall be equal to the volume of that big drop. What's the formula for the volume of a drop? It's a sphere. Volume of a sphere is 4 by 3 pi r cube, where r is the radius. So volume of all small drops, if we consider one small drop, its volume is 4 by 3 pi r cube. But there are n number of identical drops like that, small drops. So n into 4 by 3 pi r cube shall be equal to the volume of the big drop, 4 by 3 pi capital R cube. If you have noticed a little carefully, I have written a capital R, but that capital R is not known for me. So I am trying to write that capital R in terms of the small r so that I can eliminate the unknown term that is not given for me. So the relation between them from here, what we can say, this 4 by 3 pi, this 4 by 3 pi, we can be cancelled. So it's a resultant value. And this is remaining. Small r cube is equal to capital R cube. From here I can write, taking cube root on both sides, capital R is, take cube root on both sides, and power 1 by 3 and a small r. So here I have successfully found a relation between capital R and small r, and this relation is going to be handy for me to solve my further problem, right? Let's go to the problem and try to apply this formula now. Yes, let me scroll down a little. So we need to calculate work done, surface tension into area big. The small drops together will have a bigger area always when compared with the big drop. So area bigger means area of one small drop, and there are n number of identical drops multiplied by n minus area of the big drop. So work done is surface tension into n, that's the number of the drops. Area of a spherical drop, the drop is spherical, so its area is equal to 4 pi r square. I have written small r because we are handling small drops. minus area of the big drop, it's only one drop, and surface area of the drop is 4 pi capital R square. Here, as I told you, I don't know the capital R, but I have already found a relation for the capital R in the previous case. Here it is. Capital R equal to n power 1 by 3 into small r. Now I can use that relation. Yes. So as capital R is not given for me and I found it in terms of the small r and n as n power 1 by 3 and r. See here, n power 1 by 3 and r. So I can use this relation here. Substitute this in the above relation. Work done will be surface tension n into 4 pi r square minus 4 pi. In the place of capital R, n power 1 by 3 and smaller, whole square is there, therefore I should write whole square. So work done will be surface tension into n into 4 pi r square, this term, minus 4 pi, n power n by 1 by 3 whole square, that is n power 2 by 3, small r whole square, that is small r square. So surface tension, 4 pi r square, 4 pi r square can be taken out as a common term. N here remaining term is n power 2 by 3. So this is the formula that we can use to calculate the energy required to combine n number of the small drops together to get a big drop. So that's how we solve the problem simply. In the previous video, I have solved the other problem, that what happens if a big drop splits into small drops. Here I am solving what happens if a small drop combine to form a big drop. But there's a difference between that case and this case. In that case, in the previous case, as the big drop splits into small drops, the final area is more. But in this case, as small drops are combined to form a big drop, area initial is greater than area final. That means what? The area is finally not increased, but that is decreased. Area is decreased, and we need to supply the heat, supply the work. Work need to be done by us. Earlier energy is released, now energy is absorbed, and we shall supply that energy for that. How much temperature variation happens because of this? I can use a formula based on the definition of a specific heat as ms delta T. So I can equate this work done to ms delta T and find the variation in the temperature too when the other parameters are known for me. This is how we can apply the concept of surface tension and solve this small problem. Thank you for watching.